we think all the different things that might be needed, I guess, in the computer is not necessarily the top of the list. Okay. Especially when it's not coming down. Okay, ready? Yesterday, in this example, the last one we were working on, we knew 4 revolutions per minute. Revolutions. We needed to change to radians. What did we write down in our notes about the relationship of 1 full revolution and radians? So just in case you weren't exactly sure why we did what we did yesterday, 1 full revolution equals 2 pi radians, right? Now how did I use that to build a bridge? What was I getting rid of? I didn't want revolutions. I did want radians. So I went ahead and oriented my little equivalent statement to have the radians be on top, the revolution be on bottom, cancel, cancel, multiply, done. What's that? Other end. The angular speed, radians per minute. Didn't even really have to plug into the formula. I just kind of changed the units and got there. I can tell by my units with radians per minute. But if B says, uh-oh, now what? Feet per minute. Uh-oh, that's a struggle. Maybe we should look at the formula for this one, because how do we go from radians to feet? That's a little rough. So let's look at our formula, linear speed. Isn't that the little, which one, Tyler? You heard someone saying actually. There you go. What's the formula for linear speed? Mu equals what? Or do you want to say B? Equals what? Good. R. Did this one R theta over T? And technically it could be seen as S over T. But why do you think I like the R theta over T better than the S over T? Did they give me anything about S in the description? Anything about who is S again? Arc length. Did they tell me anything about arc length in the description? No, I have to go find it. But what? But what did they tell me about? Diameter. That's not R. Wait. What can I do with diameter? Okay, so I can say R is equal to 1/2 times diameter. Hold on, can we do this? 50 cents, cut in half? There we go. See, even my non-mental mathers, you can do this. So diameter is 50, then radius is 25. We cut it in half. Okay. But who's theta?
The angle.
Yeah, but what angle?
That angle.
What angle?
The angle.
But who's the angle?
That one?
Which one?
I'm guessing.
First of all, we don't like ST, right? Get rid of him. We don't like him. Second of all, hold on. We have R, right? Couldn't we rewrite this formula to be R times theta over T? Technically. Why am I saying that? Who is theta over T? Wait a minute. Isn't that just who we found?
Whoa.
So what do we have to do?
Plug it in.
Plug it in, plug it in. We can plug in our 25 what? 25 feet times our 8 pi. Now here's where it gets weird. 8 pi radians per minute. It's not going to end up being just feet per minute, is it? Unless we remember, is radians actually a unit that shows up? Now they told us radians per minute so that we made sure everything matched. But radians is an understood unit. It's actually dimensionless. That's kind of weird. But as soon as you go to feet, you actually don't have to worry about the radians anymore. Or if you want, you can still write them if you really want to. That makes you feel better. But then when we go to write the final answer, the radians disappear. They were just kind of holding the spot for a little bit for us to understand what was going on with the theta per time. But as I said yesterday, remember, radians are an understood unit. That's why in homework, when you get to one of those weird ones where it says something like, find the complement and supplement, this was a homework question, complement and supplement of the following, and they gave you something super yucky, anyway, disgusting, something like 1,
2.
and 2.
Oh,
What? Who are they? Oh,
One
90 minus 1, 90 minus 2. That's easy. What's not there with the 1 and the 2?
degree sign.
No little degree mark. What is it understood? They didn't write it. Exactly. The radian wasn't written. So radians is really a unit that's more understood and not shown. So then when you had to think, radian instead, then everything got a little bit trickier. First of all, before you even do complement supplement, you had to figure out, is it legal? Hopefully you went to go look at that picture that we drew yesterday, the day before, on Friday, of what 1 radian is approximately and what 2 radians are approximately. He has a complement, he doesn't, he's too big. But we'll get back to this one in just a little bit, because I'm pretty sure some of you had a question on that. But let's go ahead and return. Radians, understood unit. They disappear when we go. My mental mathers or my non-mental mathers, you still like money. 8 times 25. 8 quarters makes
$200.
$2 or 200. 5, 8, third. A little tricky though, right? A little tricky. I think you guys had one kind of similar to this, and I think it had something to do with a circular saw. So if you didn't get to that one, and if you get to it maybe tonight, because you're finishing up, you didn't quite get to finish for today. Any examples you were hoping that we'd have some to help? We do. This one will help with the circular saw. Okay? Let's keep peeking, because I have 2 more homework helps. Can anybody tell the big idea of what they're asking us to solve for? Big idea, we have a car with a windshield wiper. It only goes so far because you know how most windshield wipers only have like a certain range of motion, especially in the back. In the front, they cover the whole windshield. In the back, it's usually like that weird, awkward. One side's dirty and the rest is clean. But anyway, it's only rotating 125 degrees. Total length of the wiper mechanism, blah, blah, blah. What are they asking us to find?
Area of
Okay.
a sector.
Area of the sector. What's that formula? We wrote it down.
1/2
R, something squared.
R squared theta.
Alright. What do we need to plug in?
Theta and R.
I see a theta, but we don't like him the way he is. Not that we don't like him, but we can't use him in degrees. So how are we going to convert? You guys practiced hopefully last night. Who's on top? Pi. Who's on bottom?
180.
So that way my little degree marks cancel out, right? Reducing 125 over 180. 5 goes into both. That'd be probably what a lot of us would choose first, right? It would go in 25 times. And 5 goes into 18 3 times. Can we go any more?
No.
No. That's 5 and 5, 6 and 6. There's nothing. Okay, so we have our theta. I killed something.
No, if we, what would we have killed if we took the square root of the
It wouldn't be a specific animal,
Oh,
but it would be pretending like it's an equation.
that's probably what I would have done.
Because if you had square root and made it 5, 6 pi, and I understand because you're like, hey, those are both special. You would have had to write a little square root over here, and that's what you would forget. So you do that age-old, like do it to one side but not the other. It all gets messed up. We have our theta. Who else do we need?
R.
Who's R? 25?
No.
Hold on. Let's draw our little back windshield, right? There we go. And then we have our little like range of our windshield wiper, right? And then we have it turning 125, so it's there's 90 over here somewhere. Okay. So he's swiping that area of the windshield, true? Okay. What do they tell us? They tell us that is 125. We've already dealt with it. The angle. What else do they tell us? The length.
Of the wiper is 25.
Oh wait, who's the wiper?
Not this.
I'm swiping anyway. There he is.
Oh, that's right.
Oh, he is the radius. Now, I agree with some of you. I wouldn't have thought it was 25 from the way you read it either. Being like, oh, we have to cut it in half. We have to do something funny. But if you draw the picture, the wiper is the radius because theoretically, if it was to continue going, which it would be broken, that'd be a bad thing. But that would be from the center to the outermost edge. So we can call the radius 25. And specifically 25 inches. All we gotta do is picture it. I think that helped. And then plug and chug after changing to radians. So A is equal to 1/2 times 25 quantity squared times 25 pi over 36. And we're going to be awesome and just put inches squared and do something calculus kids get to do a lot called stick it to the man and say whatevs. There you go.
Yay.
What's supposed to be there? Gracias.
No.
Figure it out? Nice. Alright. Last thing. This is the one that might have stumped you in the 40s. Not 1940s.
Oh no.
40s as in the 40s-ish. On different lines. Ooh. Here, I'm going to show it this way. Okay, those are the units that you'll see. Let me start there. Those are the units that you'll see. Once you guys start writing, you just skip 3 lines. Well, 1 line is the 1 degree, and I'm going to continue over. We'll skip 2 more lines after that. No, just 3. So 1 for here, 1 for here, and 1 for here. 3 total. We're skipping 2 underneath the 1 degree part. As you guys do that, let me kind of do a best approximation of semi. And whether or not you did the extra credit last night, if we were to think of this as a protractor, how big would 1 degree be?
What?
How big would 1 degree be?
1/360.
1/360th of a circle. But I only have a half circle, so technically he's 1/80th. And then I could make it a little bit easier, and I could cut the 90 approximately. So now, how much is the first quadrant?
90.
1/90th. Did I make it any better? 1/45th.
1/30th.
1/30th.
That's
This is going to be a struggle
not
now.
a good one.
We could do
Oh gosh.
1/15.
Cut.
Right?
What did you remedy?
No,
We can't go any lower.
That'd be 1/7.5. Okay, I'm just going to go for it. Ready?
No.
Bit of a struggle. I know. It's zoomed in. I know. Stop judging.
1/360.
I had to make it so you can at least see it. Okay, let's pretend that's 1 degree. I know if you had your little protractor, it'd be smaller than that, but whatever. Question. Is 1 degree the arc length, right? The degree comes out and hits a circle, and it hits a circle at an arc length. Will 1 degree for any circle always have the same length of an arc? Will 1 degree always have the same arc?
Yes.
Why or why not?
Circle
If the circle's bigger, 1 degree is gonna do what?
Get bigger.
Okay, look at the angle, right guys? When you're in at the very innermost, you can't even see the 1 degree. And I tried to make it fairly straight. And I even over approximated. But if that's 1 degree, you can't even see it, and then all of a sudden, oh, I can actually see space, right? What's gonna happen if I keep on going out? Let's say I just went out to Lassen. That's it. Okay, let's say the circle is as big. Here's the center of the circle, and it goes all the way out to Lassen. That's not very far. Like we could walk there in what? A few seconds? Maybe if you were like really dragging. But anyway, would it be bigger than that? The little arc length that it cuts? Okay, let's say I went a mile away, a little bit bigger.
Yeah.
Let's say the center of the circle was on the North Pole.
Moon.
And let's say you took 2 protractors, put them together, and then you marked different important degrees and had them extend the length of the globe. Hey, wait a minute, that's a thing. What's the thing?
Longitude and latitude.
Latitude goes up and because it's a ladder, right? And then longitude is long. So you still don't know what latitude is. Anyway, that's what it is. Which one's which?
Longitude.
Let's say we extend it. And let's say you're lost somewhere in the middle of the ocean. And so you say like, oh, and you give a latitude and longitude and you round to the nearest degree. Wait, if you round to the nearest degree and you're like, hey, come find me, are they going to be able to pinpoint exactly where you are? Let's say you're drowning on like your raft and there's a shark. I don't know. Some movie happened recently. Anyway, so, come back. Would you want them to only know the nearest degree? A degree? Wait, but it's super tiny unless it's extended along the entire length of the globe. It's going to be a little bit bigger. So there is a purpose, especially in like GPS and navigation, etc., to split a degree, which is so tiny on a protractor, but to split it down into smaller pieces. And how do you do that? Why would you do that, GPS, when a degree is extended a lot longer than just your little circles that you have on paper? And we say, hey, we can split a degree into these things called minutes. Why is it called minutes? I don't know. We have another extra credit project for tomorrow.
No.
But my guess is, we'll say, we already did one of those. But my guess is, 16 and 1, isn't that a time thing?
Minutes.
Right? Minutes in an hour? I think they're just using because they cut it into 60ths. Why 60ths? Okay, maybe that is another thing to research. If you want, it's fine. I'll give that a print out tomorrow.
Wait, what is it
I'm
on?
curious.
What is it on?
Why are they called minutes and seconds, and why is a degree cut into 60ths?
I'm writing it down.
Maybe there's a reason. Now, hold on. But maybe you don't even want them to have the nearest minute, and you'll see how it looks like in just a second. Maybe you want that minute split down even more into seconds. So we're noting partial degrees, which if you just looked at your protractor, like sitting in a math class, you're like, this is dumb. Why on earth we want to make this little tiny thing smaller and cut it into different sections? Well, it's because, once again, GPS. We can split 1 degree into 60 minutes. We can split 1 minute into 60 seconds. We can split 1 second into, okay, that's small enough. We'll say it's pretty stinking precise at that point. We'll say it's pretty stinking precise at that point. Now let me go ahead and do an example. What if I was to give you, and this is where the number 40 is somewhere in there. They were asking you to convert maybe to decimals. If they're asking you to go to decimals, like a decimal part of the degree, they're probably giving you something like, let's do 14 degrees, 37, 37 minutes, 10 seconds. Okay, what does that mean now?
Oh no.
14 degrees and a little bit. How much of a little bit? Well, if it's 30 minutes, it's a little bit more than half. So 14 and a little bit more than a half of a degree. They want you to be a little bit more precise than 14 and a little bit more than a half. So, if we're trying to go strictly to degrees, this is a nice like split apart one. But let's say we're trying to do math with it and we're like, ew, we don't want the minutes and seconds, so we want a decimal please. You're not actually out in the ocean trying to find somebody. Okay. If we're trying to convert, question, do you really mind the 14? Yeah, he's great. 14 degrees, right? So we're not going to touch the 14. The 14's good. The 14's golden. Let me go ahead and come down here a little bit. Keep the 14. The rest of this stuff gives me a decimal. I'm trying to fill in that decimal. And we're going to have 1 degree at the end. Okay? 14. He's good. Check him off. So who's not good?
37 minutes.
The 37 minutes. I want the minutes to be degrees. Wait, look up above. Isn't there an equivalency statement that I could use to build a bridge? I have 1 degree is 60 minutes. Where are the minutes going to go if I need to cancel and get rid of the minutes?
On the bottom.
Bingo. Aha! So I have 37 60ths. Well, that's not pretty, but you know what, for right now? Since 37 60ths, we don't know what that is as a decimal, let's just write it as a fraction for right now. 37 60ths, still have a little degree.
Without calculator.
Okay? Including who? Okay, we did the degrees already, now we did the minutes, but who's left that we haven't accounted for yet? The seconds. How are we going to change 10 seconds to get to a degree? Different ways of doing it. One way is to go from seconds to minutes, and how do we do that? 60 seconds in 1 minute. That's better, but am I all the way? Need to build one more bridge. Or some of you were like 3,600? Yeah. Because now I can change 1 minute into a degree, right?
I don't like this.
You're just practicing dimensional analysis. But do you see how all the minutes and the seconds are now gone and we just have degrees? And now I have 10 over 3,600.
Are we just gonna stick it to the man?
Well, this one I actually want to see what the decimal is. But we're not going to do this in our heads. Nope. We're going to use our instruments. Go ahead. Get that calculator out. Get me a decimal, because that's what they actually asked for. If I didn't go all the way there, I wouldn't be following directions. All right. Oh, come on. You like your calculators. What's 14 plus 37 over 60 plus 10 over 3,600?
14.7 something.
Not 7. I don't think.
6 something.
0.5, 0.6?
14.619444444.
I'm just going to cut it off because we have to cut it off somewhere, right? That'd be fairly precise. But question, which one's more precise? The rounded decimal or the 14 degrees, 37 minutes, and 10 seconds? Especially if instruments are built upon the minutes and seconds. This one makes a lot more sense and they'll find you for sure. Let's start first. Okay, so. No biggie. So we're about to give you something else. Or what if I was to actually take that one and say, you know what, how close is this 14.619 degrees? Let's go backwards and see if we can retrace our steps or take a decimal and figure out what it would be in minutes and seconds and see how close we were by rounding. Okay, hold on. I need to go backwards now.
I think I know the answer.
Who do I want to keep? He's fine. Okay, the 14 degrees is fine, because he's a whole thing. I need to figure out the minutes, and I need to figure out the seconds. Alright, so hold on. I dealt with the 14. Who's left? Good. 0.619 degrees. Build a bridge. How do I get rid of degrees? Now I put the minutes up top and the degrees down bottom, right? Okay, help me out. Whoever has a calculator. Caleb, you had it earlier. Can you multiply 0.169 by 60?
10.14.
10 point what?
14.
Okay. 1 4? Sorry, guys. I was too focused on crossing out my degrees. What part of that do I like? Because let's say we had a decimal, someone was weird and gave us a decimal as to where they were, and we have instruments that have minutes and seconds. What part do I like of this?
10.
Okay, I like the 10. So let's go ahead and steal the 10 and say, okay, 10 whole minutes, got it. But what about the 0.14? That might be the difference, right? So now we go ahead and take Jason, you're tracking, right? And not distracting. Take the 0.14, except the 0.14 is in minutes. Right? I dealt with the 10 now. What am I going to multiply them by? Good. 60 who? Seconds over 1 minute. Right? We're spreading them down. Alright. Caleb, just because you've been doing it, what's 0.14 times 60?
8.4.
Can I go any lower? So hopefully, if we're at least able to do the 14 or input the 14 degrees, 10 minutes, and then 8 seconds, and then say 8.4, and hopefully it'll be a close enough approximation.
Good.
Now, hold on. How did we do then?
Really bad.
That rounding makes a big difference. Especially if you're thinking, yeah, exactly. If you're thinking that this 1 degree is going to cover a whole lot of space, maybe there's a point or a reason as to why we use those instead of those. Anyway, kind of cool idea. Now you know how to do 40-ish to the end. Let's quickly go ahead and, you know what? Let's not check our evens today.
Okay.
Let's check them tomorrow when we're going to have a little bit more time. Because I do want to get into section 4.2. We don't have to finish him today. We're just starting.
Yeah.
Can I leave?
But guys, this is a section of dum-dum quizzes. We can't leave.
Yay!
Because eventually, hopefully, you're going to get to the point to where I can say sine of pi over 3 and you're going to be over 3 over 2 and get a dum-dum. And we'll do dum-dum quizzes for a few days to work up to an actual unit circle quiz and see how we do.
Because of the dum-dum quiz?
You get a dum-dum for not being a dum-dum. Anyway, so.
So I'm screwed.
Oh.
Got him.
We're not doing a dum-dum quiz today. We haven't finished the unit circle.
Do we? Let's
We're
just
going to
not.
take a couple days on it, and then we're going to take a couple more days for you guys to be able to keep studying. And I'm going to show you 3 different ways of knowing it and being able to use it. Hopefully one of them will work. Maybe you haven't seen 3 different ways of thinking about it. And technically, there are probably a few more. I just learned of a new one yesterday. It's a song, but it's basically one of my methods I already have. Just put it to tune.
Do you have a compass that can draw a good circle? Yes.
Not a compass. Do you want to trace?
Okay. Perfect. Thank you. Oh, thanks.
However, before we get too far into the unit circle itself, we're just going to talk about its parts, its components. Because a unit circle, long story short, a unit circle has a radius of 1. 1 what? I don't care. 1 inch, 1 mile, 1 centimeter, it doesn't really matter because if you remember, radians are ratios. So are trig functions. Ratios will all reduce to be the same fraction, hence why we have trig ratios that are all the same, whether you have a little tiny circle or one that extends the entire breadth of the globe. Breadth? Circumference? Now we have these little coordinate points that really are just like any other point, except they have special meaning. With an x and with a y. If you get to any point, you go over a certain amount, you go up a certain amount. So we can, with that over and with that up, make a little baby right triangle. Right triangle. That relates to trigonometry. We'll get there in a bit. We'll get there in a bit. But long story short, when you guys memorize the equation of a circle, x squared plus y squared is r squared, maybe you didn't realize really all you were doing was writing the Pythagorean theorem. Wrote x squared plus y squared is r squared, or x minus h quantity squared plus y minus k quantity squared equals r squared. Really, all you were doing was the Pythagorean theorem. Because within this circle are infinitely many little right triangles, and as you extend, all of their relationships are the same because all of them have different x's and y's. And these coordinate points can relate to trigonometric ratios. That should be an O. That doesn't even look like an O. Trigonometric ratios. And we'll talk more about those ratios in another section when we're talking more about triangles. But for right now, we'll just remind ourselves that SOHCAHTOA, for an angle, this one corresponds to adjacent. And adjacent over hypotenuse is cosine of the angle. So whenever you have a coordinate pair, those ones that supposedly you were supposed to learn last year, the x stands for cosine of theta, and the y stands for, well, y is the opposite side to the angle over hypotenuse, corresponds to sine of theta. So for any ordered pair that you have, it has an x, it has a y. The x goes with cosine, the y goes with sine. My mind is very, I don't know, my mind's very kind of visual, kind of auditory, kind of a little bit of everything. But I always think about the xy as far as like the x is this way and it's the adjacent side of the triangle. That's why I'm able to say adjacent, that's cosine. Or the y, it's this side of the triangle, that's opposite, that's sine. That's how my mind works. Some of you might need something silly to memorize, like sine, like domain and rangey, right? Domain and rangey. Maybe sine will work because sine goes with y. What? And cosine x, I don't know.
Caucus.
Great. Sure, I broke my coccyx. Yes, don't be ridiculous.
That's not how you say it. Anyway. All of the announcement HGTV is. Anyway.
What announcement?
What? So, coming back.
Wait, what?
It's up to you. If you want to memorize sine and sine goes with the y, cosine of the other one, sine. Or sine. Fine. That's good. Or if you just want to think about the triangle, it's going to help probably a little bit later if you go into unit circle. But somehow you need to get down which one is which. And to help you to that end, technically we will write little formulas. But it's not so much about memorizing the formulas as just having an understanding of who goes with who. So, we can write these little formulas, and maybe that's a good thing to do. I'm going to have you write the little formulas.
Now?
As opposed to not.
Tomorrow?
No. Okay. What? We have 5 minutes. Put that away. Goodness gracious. Okay, so sine is what? Don't have a microphone. Cosine is x. Not feeling it. Maybe he's excited in the class to go out. Oh, you like the microphone? Oh yeah, see, I couldn't whisper. I mean, I could. Now, kiddos, hold on, really quickly, in case you're a little confused about the little t thing, just think of t as your theta, okay? It's just a snazzy way. It could be t, it could be x, it could be theta. And really quickly, if you were just to see this, sin equals 4, what? You have 4 sins? I don't get it, that doesn't make sense. Okay, no. If you write this, I'm going to have to think that you're like an Algebra 1 kid who's like, sin, I don't get it, and they don't know what's going on. Okay? What do you need to make it the trigonometric ratio sine?
Opposite.
You need an argument. Now, to be honest, this is actually illegal. Sine cannot ever equal 4. Sine is only between 1 and negative 1. Let's make it something more realistic, like 1/2. But you need some sort of argument. Otherwise, it's just sin. And that's not going to be what I want to see on your test. Right? You have to put an argument. Now, it could be theta. This is the exact same thing. No big deal. It could be an x. It could be like a, we could start using more Greek letters. They just use a t. It doesn't really matter, okay? We're still just talking about sine being 1/2 at some random place.
Wait, we could equal 2?
Oh, now I just...
Yeah, I saw that. I just figured I used up all my smart out.
It's all yours for a year.
For the year. That's intense.
I smart out a lot.
I didn't know that was a verb. Okay, so
It is now.
It's not, but I can't use the other thing.
whenever you guys are writing sine of t, just think sine of angle. So sine is the y. We already talked about that, right? Sine e. Cosine is the whatever, the x. Tangent. Now we're not talking about right triangles, although we could. But if you're just looking at the coordinate in a unit circle, tangent will be y over x or sine over cosine. That's a formula you might have learned before. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. If there's a way you need to remember this one, just think every pair only has one co. Sine has to go with cosecant. Cosine already has a co, must go with secant. And hopefully tangent and cotangent, that kind of is stuck in your mind. Now, really quickly, what if one of your ordered pairs, one of your coordinates of your ordered pairs is a 0? I could basically make a problem because secant and tangent, if you look at them, they both have little denominators of x. They're not going to work. They're going to be undefined if or when their denominator of x is 0. We have to watch out for that. And cosecant and cotangent are going to be undefined when y equals 0. But all that to say, sometimes, even though you have the little x, y in the unit circle, maybe some of these ratios will be undefined. And at times they are. Whenever we're dividing by 0. Now, what did we not do there?
Unit circle.
We didn't actually draw the unit circle. We didn't actually put the ordered pairs down. We didn't actually put the angles down. So what are we going to do?
Do it tomorrow.
Tomorrow, woo! We're going to make this thing. But wait,
Tyler,
question.
sorry.
Am I the kind of teacher that says pi is a half circle, memorize it, alright, let's move on.
Yes.
What did I say pi was?
Calzone.
A calzone. And what did I say for you to think about if... I still have 25 seconds. You guys are robbing me blind. Come on. Okay, I said pi, as in the Greek letter pi, as in 3.1415926 radians, is a calzone, right? What was the point of that?
It's half.
If you cut the calzone in half, how much pi do you have?
90.
Half pi, pi over 2. If you cut the calzone in fourths, how much if I have this much of it? Wait. If I cut it in fourths, how much if I have this much?
Fourth of a pi.
3 pi over 4. Tomorrow we're going to build a unit circle based on fraction. Hopefully you'll remember. Bye guys.
For the record, let's do it. Anybody go back a page really Yeah, Tyler, why do you have it? Yeah, yes, the numbers at the end in the boxes, right?
Hey, what?
I was saying the fourth at the end in the boxes, right?
Where are you going?